Alright, so this is chapter 2. Okay, so before I start the lecture for the chapter 2, so here we have 8 picture. What come to your mind when you look at all these pictures? So you can see the symmetry there. So like this one, you have the mirror symmetry, 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 symmetry. Yeah, you are right. So in this chapter, we're going to study the symmetry of the crystal. Okay. So have you ever wondered what is inside the Panadol? Okay, everyone know Panadol, right? But have you ever wondered what is the compound of the Panadol? Okay, and what is the structure for the ibuprofen? Okay, when you feel pain, then you can take a tablet of this ibuprofen, then it can relieve your pain. Okay, so these are the structure of the Panadol and ibuprofen. Okay, why do I want to introduce these two structure? Because this is the thing that we are going to study later on, okay, in chapter 4, chapter 5, X-ray crystallography. So in that chapter, I will introduce how do we determine the structure, okay, the structure for all the natural product as well as the synthesized product. Okay, so a few years ago, there's one virus we call Ebola. Okay, so have you ever wondered how does Ebola virus look like? Okay, this is the schematic diagram. It looks like this. But how do we know that it looks like this? Okay, you have to go through the crystallography process. And one of the main component or key component of the crystallography process is symmetry. Okay, so therefore in chapter 2, I will introduce you the concept of the symmetry. Okay, so this is the schematic diagram of the Ebola, and this is the crystallography result of the Ebola, and we also call this crystal structure. So you can see that this is a Ebola glycoprotein 1, 2, and then the antibody heavy chain, and so on and so on. Okay, so they crystallize the Ebola protein, and then they use the X-ray crystallography method to determine the structure. Okay, why do symmetry important in crystal? Why do symmetry important in crystal? Okay, you can see this green atom. Okay, in fact, this green atom has a very small size, which is in the angstrom size. Okay, that means that the size of this atom could be 4 angstrom times 4 angstrom. Okay, we take it as a square. Okay, 4 angstrom times 4 angstrom. It could be smaller, like 2 angstrom times 2 angstrom. So in one small crystal, let's say 1 cm times 1 cm, you can calculate how many atoms inside this 1 cm times 1 cm crystal. It's million to billion. Okay, so therefore, it's not possible for us to determine the whole structure, the big structure, if the structure is not arranged in order. Okay, it's not arranged in order. So I believe you have studied in the last chapter what is the definition for crystal. Crystal means basic plus lattice, and all the atoms have to be arranged in order, right? So this is another picture of the protein structure. So this is the schematic diagram of the protein structure. Okay. So just now I mentioned that in 1 cm times 1 cm of the material or sample, there are billion atoms inside. Okay, so there's no way that we can determine the structure for this sample. Okay, there's no way that we can know that how the Ebola look like. Okay, how does it look like? No, unless this sample are crystallized as single crystal. Okay, so when I mention single crystal, that means that it has lattice plus basis, right? Lattice plus basis. So all the atoms are arranged in order. Remember that in last chapter, I keep mentioning order and repetitive. Repetitive. The keyword here is repetitive. So repetitive means that, let's say, it's arranged this way. So once I determine the structure of this portion, then the rest of the portions should be exactly the same. I don't have to determine the whole structure. Why? Because it's repetitive. It's repetitive, so I just need to determine the smallest unit, or we call this unit cell. Okay, so the unit cell could be very small. Let's say like 5 angstrom times 5 angstrom times 5 angstrom. Instead of you want to determine the structure of 1 cm times 1 cm, which is not possible. Not possible in terms of the computation power and so on and so on. Okay, so at this moment, not able to do so. Therefore, the repetitive arrangement is very important in determining the structure. Then the next question is, are all the atoms always arranged like this in the proper order? The answer is no. Okay, because this one you can see that it's only involved the translation. This atom translate to this atom, translate to this atom, translate to this atom. But in the real case, the symmetry not only include of translation, but it also include other type of the symmetry, which I will explain in this chapter. Okay, so this is another type of the virus, typhoid virus, and this is how the protein structure look like, and this is how it look like under the microscope. This is under the microscope, and this is under the diffraction. Okay, diffraction image. Okay. So symmetry could be very easy, but combination of symmetry could be very complex. Okay, so there are many types of symmetry like fold, rotation, like 2-fold, 4-fold, 6-fold, 1-fold, and so on and so on. We also have the mirror plane. We also have inversion point. We also have translation point, and so on and so on. But when we combine all these symmetry together, then the situation or the case will be much more complicated. For example, this is the symmetry of, this is the state group I for